Welcome back to our lesson number 5 in this module. And on this part of the lesson, we are going to be strictly looking at our delta to star conversion. And we usually do this type of conversion or transformation, as they call it, in order to allow us to simplify or analyze a circuit in a much better way. And you will see in the exercises that come. So what happens that you are given a delta system as known or as you see on the left hand side, and we want to transform that into a star system, which is on the right hand side of my arrow. So what we do is we take that star system that we want and you embed it inside your delta system that you have been given. And then in order for you now to work out what your ZA, your ZB, and your ZC are going to be, you multiply the impedances on the delta that are adjacent to the star you are looking for. What do I mean by that? I mean that is the impedances that are right next to it or are sharing the node where your star impedance is connected to. So if you look at ZA, you can see ZA comes from node A, and also from node A, you've got ZCA and ZAB. And you can clearly see that those are adjacent because they are next to your ZA. And then obviously your total will be your ZAB, your ZBC, and your ZCA all together. So ZA then would be equal to ZAB multiplied by ZCA divided by the sum of all three. Your ZB would then be, you look at your node B and you can see that coming from node B, you are going to get your ZB that you're looking for, and you've got ZAB and ZBC. So therefore, it's ZAB times ZBC divided by the sum of all your delta impedances. Then you go to ZC. You can see it's coming from node C, and at node C, you've got that ZC you're looking for, and then you've got ZBC and ZCA coming out. So therefore, to get your ZC, it would be there, ZCA times ZBC divided by your total sum of your impedances on your delta system. We are now going to look at an example where we are doing a transformation of our delta to a star and finding the equivalent impedance to this circuit that you see here. Now, what you must notice about this circuit is that you've got two delta systems in one, all right? So there's a top triangle and there's a bottom triangle that's sharing that 100 ohm impedance. So what you need to do is you need to, in your head or on a piece of paper, you draw in your star system inside the top delta triangle. We'll start with the top, all right? And when you draw it in, you can now work out your ZA, your ZB, and your ZC. So on the side, I've put now the formulas that say your ZA is equal to that ZCA times ZAB divided by the total. And what does that really equate? It's your 40 multiplied by 60, then you divide by the entire sum. That gives me 12 ohm for ZA. Then I go to my ZB, and my ZB will simply be my 60 multiplied by my 100. I divide by the total sum. I get 30, and then my ZC will simply become my 40 multiplied by 100 divided by the total sum, and I get a 20 ohms. So now I can redraw the second top section, and that is how I do the redrawing. So you see on the far left is what I had originally, then I redraw it now with the impedances that I've got. So the top triangle has been replaced, it's no longer there, and I've got my star system in. Now what do you notice? Now that I've got a star system in here, I then move on to the circuit close to that on my right hand side, where I have added my 20 ohms and my 100 into 120 because those are impedances in series, and then I've added my 30 and my 90 to be another 120 because they are also in series. So I've got two in series impedances of 120 each, and then I've got a 12 ohm, which was my ZA in the system. So therefore now I know the two parallel I can combine into one impedance, and that gives me a 60 ohms, and then I had that 12 that they were in series with. You add those two up and you get that my equivalent is 72 ohms. So I had done this now looking at the top triangle. We're now going to try it looking at the bottom triangle. So here it is now that I am going to do the bottom part of my delta circuit. So I find my star inside my delta circuit. You can throw it in very small so that you can be able to calculate those impedances on the side. So my A would be the 90 times the 100 divided by the total sum. My B would be the 100 multiplied by the 100 divided by the total sum, and my C would be the 90 times the 100 divided by the total sum. So I get a 31, a 34.5, and a 31 ohms. Now, if I look on the left-hand side, okay, my 40 ohms and my 34.5, I add it as one impedance because they're in series. And then my 60 ohms and my 31, I add it into one because they're in series. And then those two would be parallel with the 31 in series. And that takes me to this next slide where I've now added those impedances. I've got the parallel circuit plus the 31 that was my ZA. I then combine the parallel circuit and I have that 31 to add it to, and you can see that I still get the same value of 72. So what am I saying? In this scenario, it didn't matter. You were able to make your own choice. You could have chosen the top triangle or the bottom triangle to work out your solution, and your equivalent impedance would have still been the same at the end. That's what I was trying to prove for you. So here we have an example from our textbook where you are given a delta system, and then you have an impedance that is going into the delta system on your A phase and one on your C phase. There isn't one on your B phase, but you've got your supply going connected on your B phase. So they ask us in the first part of the question that we calculate the total impedance of this network using our delta star conversion, and then once we've found that, they want to know what is the current that the system is drawing currently, and they've given us that the voltage is 380 volts. So the first thing that you do in this instance, you go and draw in your star inside your delta so that you can be able to work out what those impedances will be. And there you can see I've actually gone and put in my star system inside. So if I had to work out my ZA, I know that it would be there. ZAC multiplied, or ZCA multiplied by ZAB, then I divided by the total. My ZB would be my ZAB and then multiplied by ZBC divided by the total, and then my ZC would be my ZCA multiplied by my ZBC divided by the total. So now that you've worked out your ZA, your ZB, and your ZC, you come on to this part where you put in the impedance that was going through to A and the other impedance that you already given in the system. Then only you draw out your star connected impedances that you have just worked out. Then looking at this and simplifying it further, you can see that your ZA is in series with the impedance that was going through to your A node. So you can add those two up. And you can see again, looking from the neutral point of your star system, that your ZC is in series with the impedance that was going through to your C node. So those can also be added up together. And then that will give you a parallel circuit, which you can see on this slide. So I've got that Z, I'll call it ZAA as the impedance that was going through to my A node plus my ZA. And at the bottom, I can see that I've got my ZCC, which was the impedance going through to C, as well as my ZC that I worked out. And then those two are in parallel and they are connected to your ZB. Then the two in parallel, you can do the parallel equivalent of that circuit and get one impedance, and then I've got it in series with my ZB. So therefore my Z equivalent will simply be that two impedances that I add together. And that is how your circuit at the end of this would look. And then you simply know that in order for you to now calculate your second part of the question, which was your current drawn by the system, you utilize your Ohm's law, where you know that your current is equal to your voltage and you divide it by your impedance. Are we clear? So I didn't put in all the sums. You need to go and put it all of them in and work out the impedance of this circuit. So what I've done now is that I've gone out and looked for another example that we can utilize so that we get more practice onto this delta to star conversion. And I've put in something here from the textbook on exercise 2.2, number 13. And in this network, you can see you're given a delta network. And on this delta network, you're given impedances on your A phase, your B phase, and your C phase going towards the delta network. So what they're saying is that they give you the voltage of the system. They tell you that we've got EBC as reference with a positive phase sequence, and they want us to calculate the line currents drawn by the system. Now you must remember what are our line currents. Our line currents are IA, IB, and IC. So how do you go about doing this? Well, the first thing you do, you go into your delta system and you put in your star system. And that is what I have done over there. So that will allow you to work out what your ZA, your ZB, and your ZC are going to be. And you know that your ZA is simply going to be your 13.6 multiplied by the 15.7 divided by all those impedances. And your ZB is going to be the 12.1 multiplied by the 15.7 divided by all the impedances, whereas your ZC is going to be the 13.6 multiplied by the 12.1 divided by all the impedances. Do not forget the angles. So once you have calculated your ZA, ZB, and ZC, you find your ZA total, ZB total, and ZC total as shown on the slide. You find your voltages looking at your positive phase sequence. And then comes the part where you go and find, remember what we called our VSN. Why is it important to now go back to VSN in Millman's theorem? Because we are working with a star load. Okay, so therefore it means that I've got a floating neutral. You don't necessarily have that EAN at this point in time. So you find my VSN, which means I can find my VAS, VBS, and VCS. And that will finally allow you to find your IA, IB, and IC. So guys, it's a very long exercise, but I want you to try and do it and see what you come up with as your answer. Then, as the last part of this lesson for today, is to go to your tutorial and look at question number 6. All right. So the first thing I want you to note is that there was an error on the tutorial. It was not ZA, ZB, and ZC that you were given, but ZAB, ZBC, and ZCA. All right. And it says you must use the delta to star conversion to calculate your line currents. I know it said that the power dissipated in the system, but for where we are at this moment in time, you're only ready to calculate up until your line currents. So do that. Then the next step, when you've done the power, you can do the next. Thank you very much. We will see you in the next lesson.